So we're looking at changes of state. It relates to thermodynamics because we're still adding heat to a system in order to change the state. So if you had a solid and you wanted to melt it, you would add heat. And as you're adding heat, you can see the temperature is going up of that solid until the particles they're vibrating more and more as the temperature is going up, until at this point the temperature is constant and all the heat you're adding goes to take them from being these solid particles that are stuck in place to being liquid particles that can move around each other. And once you have all of your particles, all of your solid melted, at this point we can start to heat the liquid. So we have a liquid, we're adding heat, and as we add heat, the liquid goes up in temperature until you get to the point that now you're going to be evaporating this liquid. So your liquid particles are moving faster and faster this entire time until they get to a point that they're moving around and all the heat you add doesn't increase the temperature, but it separates the molecules into a gas. Okay? And then at this point, as you add heat, the gas gets higher, the temperature of the gas gets higher and higher. So here's some values. This is the heat of fusion. That's going to be the heat required to melt the ice. Here I have the heat of vaporization, and that's the heat required to evaporate the water, to vaporize the water. And I can see that I have kilojoules per mole, so I need to know how many moles of this substance, and these are both for water. These values I can only use for water. If I wanted to melt another substance, I'd have to have the heat of fusion or the heat of vaporization for that substance. I also have the specific heat of water for ice, for liquid water, and for steam. And whenever I'm doing this, I can see I have a temperature change. And so if I'm changing the temperature of something and I have the specific heat and I know how much of the thing I'm changing temperature of, I know I'm using this equation, Q equals C M delta T, and that's going to be any time the temperature is changing. So really what you do in these problems is you look at where you're starting. Let's say I'm going to start here, and I'm going to finish here. And then you ask yourself what has to happen. Well, I have to melt this ice, and then I have to heat this liquid, and then I'm going to vaporize this liquid until it's a gas, and then I'm going to heat this gas. So you actually have to calculate each step. So this would be, actually probably start at the very beginning. This would be how much heat's required to melt the solid, and then how much heat is required to heat the liquid, and this is how much heat is required to vaporize the liquid, and this is how much heat is required to heat the gas. So you'd be using each one of these to do each of those 4 steps. So here's an example. These examples are good. We have how much energy would have to be added to heat 10 grams of ice from negative 20 degrees Celsius to water at 25 degrees Celsius. So I know I'm going to, first I'm going to have ice, I'm going to heat ice, and I'm heating the ice from negative 20 all the way up to 0, because once I'm at 0, I'm going to melt. So that's the first step. So I can see that I'm changing the temperature, which means I'm going to use Q equals MC delta T. So the joules I'm going to use, Q equals the mass, which was 10 grams. Whoops, that's an M. I wanted to write 10. 10 grams. The C, the specific heat of ice, 2.1 joules per gram degree Celsius, times the change in temperature. I'm going from negative 20 up to 0. So I go final, 0, minus initial, negative 20. So that's a change in temperature of 20 degrees. And I go ahead and calculate that, and I'll get it in joules. It's 420 joules. My other values are going to be in kilojoules, so I'm going to go ahead and convert this to kilojoules by dividing by 1,000. So 0.42 kilojoules. Okay, so that's the first step. Now I have heated my ice up to the point where it'll start to melt. So that's the next part. I'm going to melt my ice. And when I melt the ice, I can see that I'm going to need the heat of fusion. So, and this is in moles, I know I'm going to have to take these 10 grams of H2O, and I'm going to have to convert the grams to moles. And once I have moles, I know how many joules I'm adding, or how many kilojoules I'm adding in order to melt them. So I'm going to say for every 1 mole of water, I I add 6.01 kilojoules. Okay, and when I multiply that, I'm going to get that. I just added 3.336. So 3.336 kilojoules. Okay, so now I've melted my ice and I have water. I have water at 0 degrees, and I'm going to heat that water up to 25 degrees. So this next step is heating water. So I know since I'm heating it, I'm changing temperature. I'm going to use Q equals Cm delta T. So I know the specific heat of water is 4.184. And that's joules per gram degree Celsius. The mass of the water that I'm heating is still 10 grams. And the change in temperature is from 0 up to 25. So final minus initial, it's going to be 25. And I can see grams and Celsius cancel out. I'm left with joules. And I'm going to turn it into kilojoules, by the way. So I'll take this answer and I divide it by 1,000 to turn it into kilojoules. And I get 0.1046 kilojoules. And I add these three amounts together because I put in kilojoules to heat the ice, and then I put in more kilojoules to melt the ice, and then I put in more kilojoules to heat the water. So I added all of these steps up, and I get 3.86 kilojoules. And I rounded to this point because, let's see, here, I did know this to this number because I had 2 sig figs here. Oh no, I only have 1. Oops. So I know everything to the tenths place. Let's see if I have 2 sig figs in the second part. Temperature doesn't limit me in the second part, this does. So I know everything to the tenths place. So I'm going to round this to 3.9 kilojoules. Okay. So that is changes of state.